Okay, well, this is the third in our new starter training. We build it new starter training, but as I've said before, everybody's welcome to come along, and please do ask questions as we go. The more interactive we make it, I think the more successful the sessions are. So without further ado, let's have a quick recap of what happened last time. So hopefully you've seen it. If not, they are all available. If you go into YouTube and search for Genius Energy Lab, they're all available there. Last time we covered how ground loop design works, the factors that influence borehole requirements, spacing and so on. Talked about the natural resources that we can exploit, talked about borehole design and detailed layout. We did a demonstration of how the design actually works. And then we talked about more salesy type stuff, which is around the types of information you would like you to get from the client to then help us be more accurate with our building load, our ground loop design. We talked about the benefits of balanced heating and cooling loads, so just recharging the battery, putting some energy back into the ground. And it might not be just cooling loads, there might be other sources of heat as well we touched on. And then we finally talked about the data that can make design more accurate, which segues very neatly into session 3, which is today, where we're going to talk about one of the main things that you can do to make ground loop design more accurate, which is thermal response testing or conductivity testing. We're then going to go on and talk about pressure drop, because that's one of the biggest and most difficult really bits of ground loop design. That will then lead us into headers and how we connect all these things together. And I'm going to touch base for a few minutes on pushing the limits of pressure drop. So that's really looking into the future, looking into the challenges we've got with current systems and where we're likely to be driving systems for the future. And then finally, just to finish up, I'm going to talk about our initial geology report that we provide for Kenza, what that's for, what its limitations are, what we put into that report for you, and then just have general discussion thereafter. And then just before we start properly, there are a couple of follow-up sessions coming. Session 4 is on risks, so we're going to talk about how we mitigate the risks we look for. We're going to talk specifically about the risks associated with open loop systems, but a lot of that session, once we've kind of dealt with risks, we're going to deal with a Q&A. So if you haven't seen all of the sessions before next week, then it would be a good idea to have a look at them, or even have a recap of the sessions if you've got time, so that you can make a note of any questions that you haven't had a chance to get answered yet. And then finally, we are going to have a session 5, which is on mines. That's a rerun of a session that I did for Kenza's conference last year. Obviously, a lot of new starters since then, and we didn't record that conference presentation. So I'm going to do a rerun of that to bring you up to speed with how we can engage with mine water as a source for ground source. So without further ado, unless there's any comments or questions in the chat, Duncan?
None at the moment, so you can crack on.
Okay, excellent. So thermal response tests, a bit of nostalgia for me. This is the first thermal response test or conductivity test box that I built with the Sparky that was working with me at the time, and it was around 2001. We built it, and to show you the vintage, this here is not a CD-ROM drive. For those who are familiar with a 3.5-inch floppy drive, was the state of the art at the time. So that gives you an idea about how long ago it was. Anyway, I'm going to talk about what's inside this box. This is a fairly Heath Robinson type of affair that we built, but it worked, it did the job, it's very accurate. So firstly, when do we do conductivity testing? I guess there's 3 times in a project's life that you would do conductivity testing. First is never. You just don't do a test. The second would be on the first borehole once you start drilling the production bore field. And the third time would be in advance. So you've got a specific mobilization of a drill rig to go to site, drill a hole, do the test, come back off site again, and then go back, presumably then to do the final bore field. I did touch base at the end of last time on marking a rule of thumb for that. If it's 0 to 10 boreholes, then it's probably not going to be justifiable to do the cost of this test. Tests range 2.5 to 3,500 to do the physical test on site and process the results. So to offset that in a 1 to 10 borehole system is probably unlikely. On a 20+ borehole system, then it is almost always a good idea to do a test, at least on the first borehole. And depending on the appetite for financial close on the project, it might be worth doing a mobilisation. Now, a whole test costs between 15 and 35,000. And a good deal of that is mobilising the drill rig to site. So it's worthwhile bearing that in mind. And you'll notice I missed over a 10 to 20 borehole range, and it's a real judgment call in that area. You might save some money by doing a test, you might not. So again, it's a judgment call depending on everything else. I'm going to talk at the end of this first section on the benefits, so you can hopefully start to see why you might decide on a 15 borehole project, why you might do a test. So that's the when. Any questions so far, Duncan?
No, none at the moment. So
all right.
If you have any questions, please type them in.
Yeah. Okay. Why would we do a test? So this is an example of a ground condition that we might find. This actually is what you tend to find under London. It's called the Thames sequence. And on the top here, you've got the London clay. You've then got the Woolwich and Reading beds and Thanet sands beneath, and you've got the chalk underneath. Oh, I can't write. And the chalk underneath. Okay. The London clay is just what it says, it's clay. They actually dig this stuff up, they quarry it to be used as pond linings. So it's a malleable clay like you make pots with. The Woolwich and Reading beds are sands and gravels. Beneath that, you've then got the Thanet sands, which are a very fine running sand. It actually moves around. And then you've got the chalk. The chalk is quite variable, actually. Chalk is predominantly limestone. It's formed out the skeletons of old sea creatures. And depending on whether the sea was very clean, not full of silt, in other words, it will be very close to a pure limestone. But more often than not, it's got quite a bit of silt in there that's been crushed in with the limestone. And so it'll be what's called marley chalk. So it's got an element of clay and mudstone in there. So hence the variability on the conductivity. So 1.7 to 2.8 is the type of variability we find in the chalk under London, which is watts per metre per Kelvin. It's a direct measure of how much energy we're going to get out of those boreholes. And it's one of the parameters we're trying to measure in the test. So because we've got various different levels with different conductivities, and because we've got various different conductivities even within the types of strata themselves, a conductivity test will allow us to measure, first of all, the thermal conductivity, also the undisturbed ground temperature, and really importantly, it allows us to establish what the drilling conditions are. So is it more economic to drill to 200 metres in this site, or actually are we wasting our time trying to get that last 10 metres on the borehole because of whatever ground condition? So that's why we're doing it. We're trying to ascertain the ground conditions and the most economic drilling depth and thermal characteristics of the ground. One final complicating matter is in the top of the chalk here in London and in other aquifers like the sandstones under Manchester, we've got water. And that water might be moving around. In the chalk, it's in cracks and fissures, as I've tried to show there. In the sandstone, it can just be moving through intergranular flow is what it's called. So it's actually moving through the rock itself. So that can have an influence on conductivity. And again, I've tried to show you here, just by drawing it, that if we're on one part of a site, we might have more London clay than on another part of the site, for example. We might have cracks and fissures on this part of the site and not on this part of the site. So we can have variability across a site. We try and assess whether that variability is going to be significant on the project. And it tends to be when we get very high conductivity numbers, higher than we were expecting, that we have to take a view on how much credence we put into that test. Okay. So we're trying to gather quite a lot of information about to answer that question. Why are we doing the conductivity test?
Ian's posted a comment that for a recent quote for a 300 metre deep conductivity test, with the drilling alone being 29,000, which, to be fair, for a 300 metre deep borehole, there aren't many, if any, other drillers capable of going to that depth. Certainly within our market space. So I'm not surprised it's quite a hefty cost per metre for the drilling.
Yeah, 300 drilling to 300 metres is a challenge, for any driller. I mean, talk to an oil well driller, they'll laugh at you because they're drilling to many kilometres. But with the rigs that we are using, with the techniques that we are using, it is a challenge. But thanks, Ian, that's very, very helpful. How on this? So how do we do the test? So we drill a hole, and that hole needs to be to the depth that we are anticipating drilling the production well field. And the reason is that we're actually measuring a weighted average across these ground conditions. So if we drill deeper, in this instance, we'd have more chalk to deal with, and the conductivity of that would start to predominate. So we've got to be drilling to approximately the depth we expect. Now, that's not to say we're not experimenting and learning as we go on that. So, for example, we might drill a test bore to 300 meters, but actually that last 40 meters was a nightmare. So we install the loop to 260 meters and measure that. So there are some variances in that, but ultimately the bottom of that loop wants to be where we're going to be putting the bottom of the rest of the ground loops on this site. Okay. At the top, we attach a box, which I'll talk about in detail in a second, and we connect it to the loop with very well insulated tails. What we're measuring here is the amount of energy we're putting into the hole, so we don't want to be losing it to the air around. The other component on it is this horrible thing here, which is a generator generally. If you can get power, and mains power on a site, then that is by far the best solution. You need something like 12 kilowatts for most boxes, so it's a fairly hefty power supply. You very often have to take into consideration, is this a construction site? So is it 110 volt only, for example? So lots of considerations there. Most of the time, however, you do have to use a generator. And generators run out of diesel, they surge, so the power isn't nice and clean, all sorts of problems. So that's the main of the issues you tend to find on site, is just generators misbehaving themselves. Other issues you have, practical stuff like security. Nice shiny stainless steel box might attract unwanted attention on a site. So you do have to consider those elements as well. And you do have to have somebody there in attendance pretty much for the whole duration of the test, which is 48 hours. And I'll talk about that again in a second. So if we zoom in on the box, what we've got here is this is the water coming in, and that's the water going out. We've then got this thing here, which is an electric boiler. And we use that to inject heat into the loop, and I'll talk about that in a second. We've got a pump here, which drives the fluid round the loop. We've got a power supply, which is delivering power to both the electric boiler and the pump. And hopefully all the energy that's going into that electric boiler, plus all the electrical energy that's driving the pump, ultimately ends up as heat in the loop here. And so we measure that with an electrical meter. Now, one of the reasons we measure it electrically rather than trying to do some kind of heat metering on it is that actually measuring electrical consumption is a very accurate and very easy process. So we simply squirt the electrical energy output into a data recorder, and all the rest we have to measure is the temperature coming back from the bore field and the temperature going out to the bore field. And again, you can measure temperature in a fluid very accurately. Notice we're not measuring the flow rate because that is a much less accurate process. So this test processing that we do is designed so we don't have to measure flow rate. So we simply measure the electrical energy into the loop and the electrical energy into the pump, and that's the amount of heat going into the loop and the temperature change that then causes in the loop. The procedure is we set the thing up, we flush and purge all the water, all the debris and air out of the loop, and we set the pump running without the electric boiler on. And we run that for about 30 minutes so that the temperature in the ground temperature down here stabilizes with the temperature in the fluid. Okay, so what we're doing there is we're measuring very directly and very accurately the undisturbed ground temperature. We then turn the electric elements on, and these generally come on in stages, and we'll try and match the thermal input from that electrical heater to be approximately the same as the energy output we're expecting from a single borehole at that location. It's not critical, but it's good practice just to keep it about the same. We then run the test for 48 hours, and we get the data off the data recorder here to back to the office where we process the results. So what's the benefit of it? And incidentally, this is a just a random TRT test that I picked some data out of this morning, and that's one of the processes that we go through to process the data, is to fit curves to this to see what the gradient of it is. This is temperature here, and this is the logarithm of time along the bottom. If anybody's interested in getting into processing it, we might run a future session on how you process the data. So the benefits then, generally, and I mean 80% or more of the time, we are reducing the ground loop. As I've talked about in earlier sessions, we are making a desktop assessment, and we'll come back to that when we talk about initial geologies later, but we're making a desktop assessment of the thermal characteristics, and naturally we're being a little bit conservative because we don't want to over-egg what we're expecting the conductivity to be. So well over 80% of the time we get a reduction in ground loop. The rest of the time, almost all the rest of the time, it's about the same as what we expected. So with some tweaks, we're okay to go. And in a very, very small minority of the time, we get a disappointing TRT test back. Okay, so that we're generally reducing cost. Because we're reducing ground loop, we're obviously saving cost in the installation. It's an interesting point when you're doing the TRT test on the first bore on a site. There's nothing like a TRT test box appearing on site to speed drillers up, because they want to get as much pipe in the ground before you tell them to put in less, because that's how they get paid. So it's an interesting one, that. And then finally, the final benefit of TRT test is peace of mind. You know, if you're talking about a very big project, the cost of doing a test either in advance or on the first bore is relatively insignificant compared to the potential costs of having to go back and put more boreholes on, which, as I say, is very unlikely, but it could happen. So that's thermal response testing. Have we got any questions on that?
No questions in, no.
Okay. No problem at all. So let's go on to talk about pressure drop. So this is probably the most challenging bit of ground loop design. Session 2, we covered the how much pipe do we need to put in the ground. This is how it all hydraulically connects together and how it hydraulically works. And the main part of that is pressure drop. So let me explain what pressure drop is for a start. So we pump fluid around our loops, okay? Stating the obvious, really. What I've got here is a little drawing of an EVO and an external pump, and obviously the EVO actually has an internal pump, but I've just done it with an external pump just to be really clear about what's going on. And when we're pumping water around the loop, there is friction in the process. So mainly along the surface of the pipe here, but also within the fluid itself, there is friction going on, and that causes. That means that you need some energy. If you've got friction, you're going to need energy input to overcome that. And the energy is provided by the pump. And this is done by pressurizing the fluid. So it provides that energy into the fluid by pressurizing it on the outlet of the pump. Okay. If we look at this, then pressure 1 here going into the pipe is going to be bigger than pressure 2 coming out of the pipe. So the pressure is falling along the loop, pressure drops along the loop, and hence we call it pressure drop. And if you've sized your pump properly, the pressure drop will equal where the pump is on the curve at a loop. And just to note that we're measuring pressure drop in kilopascals. Okay, if you work in air distribution systems, you'll be working in pascals. The pressure drops are much smaller in air systems because air's lighter. It's easier in that regard to move around. So that's how pressure drop works. It's simply the pressure induced by the pump to overcome the friction that's caused by the fluid running through the loop. Now, there are other complicating factors. For example, is the fluid in this loop flowing really smoothly, so it's a laminar flow, or is the fluid in a turbulent flow regime? That has a big effect on pressure drop. So there are some subtleties to it, but if you just bear in mind, it's overcoming the friction in that loop by putting some pumping pressure in, and that pressure reducing along the loop, hence pressure drop, then that's really the main parts of it. Okay.
Cool. Alistair's in with a question, just going back onto the thermal response tests.
Yeah.
Is the hole that is drilled and tested always used in the ground array?
Almost always, yeah, almost always. I've known them to be damaged beyond repair in the time between the test and the start of the production bore field. I've known them to be just lost on site, not so much now that we use very accurate GPS to locate things. I've also known one that was a test bore to be hit by the drill rig when they were drilling the hole that was in approximately the same location. So most of the time, yes, and obviously you want that to be the case if at all possible. Okay.
Yep.
No other questions?
No, not for the moment.
Fair enough. Okay, so that's how pressure drop physically works. But what influences that pressure drop? This is a pump curve, and this is what we spend our time trying to establish is how much header can we overcome given the flow rate we want to achieve. So we're trying to achieve something like 3.2, 3.3 litres a second in this, and we're trying to overcome 80 kilopascals a head. And this is size and software from Grundfos, which allowed us to select that Magna pump, so that we're effectively selecting it to equal the pressure drop in that loop. So what are the influencing factors on this? Higher flow rates mean higher pressure drops for a given pipe size. Okay, so if we've got a higher flow rate, we will have higher pressure drops. Smaller pipe also means higher pressure drop. So if our pressure drop is unacceptably high, we may be able to reduce the flow rate, and there are ways we can do that. We may be able to increase our pipe in terms of the borehole collectors and the headers, and I'll come back to header geometries in just a little bit. Most of the time, though, we are fairly restricted in terms of how we can change that pressure drop. Most of Kenseth's heat pumps are published with an optimum flow rate and a minimum flow rate, which is about 80% of that optimum. And if we are looking at, say, a block of 20 flats, or let's say 10 for easy counting, a block of 10 flats, if we were designing it for all those 10 flats running all the time at optimum flow rate, you could say we would be over designing the system. So we can take a rational view and say, well, actually, if 80% of them are running, then let's design it to that maximum flow rate for, so if 8 units are running, let's design it to that optimum flow rate. But if more than 8 are running, let's drop it down so that when 10 are running, we're at 80% of that flow rate. So therefore hitting the minimum on that unit. Now the effect that has is that because we don't have the guts in the pumps to pump at the velocity we want to, it will be reducing the flow rate, and therefore it will be increasing the temperature difference across the heat pump. And if you want to see why that is, back in the first and second, particularly the first session, we talked about delta T's and flow rates and that. So we've got some control in terms of utilising and sizing our pipes. We call it pipe sizing, is how we keep that pressure drop acceptable. The other point I'd make while I've got a pump curve up here is that the pumps internal to heat pumps tend to be relatively weedy compared to external heat pumps that would be put in a plant room. And that's because the heat pumps tend to be designed to cater for a reasonable amount of loop configurations and generally smaller loop configurations. So 80 kPa up to maybe 120 kPa will be typical for the power, the pressure power that a pump can exert on an internal heat pump, internal to a heat pump, sorry. And I'll come back to why that's relevant in a minute. But when we're talking about bigger plant room projects where you've maybe got a central set of pumps that are driving multiple heat pumps, then being up 200, 300 kPa is not unreasonable in those environments where you've got a specific pump to select. Things that influence the pressure drop is the properties of the fluid. So the viscosity of the fluid primarily, how viscous it is, how thick it is important in terms of taking that account in what influences pressure drop. Also bends, elbows, if the pipe's been kinked or whatever, that can have effect on pressure drop. And then the heat pump requirements and characteristics, they are one of the big influencing factors. So the heat exchanger inside the heat pump will have a pressure drop in and of itself. You can imagine it's resisting the flow of water through it. So the characteristics of that heat pump are important. And the heat pump requirements, what keeps that refrigeration cycle that we talked in session 1 what keeps that refrigeration cycle in the sweet spot gives us our flow characteristics. And that's what the R&D folk in Kensa heat pumps will be doing for the new products that are being developed. So bottom line on this is higher pressure drop means more pumping energy. You can't get away from that. The higher the pressure drop, the more pumping energy. What you're trying to do is manage that pressure drop down, either to be within the capabilities of the internal pump, or more commonly, to stay within the 3% rule. Now, the 3% rule is written inside the standards for ground loop design that we adhere to in the UK. And what it means is that your pumping energy in terms of the electrical consumption of that pump over a year should not be more than 3% of the thermal energy that is delivered by that system in the year. Okay, so 3% sounds like a tiny amount, but with modern pumps, it's actually quite easy to achieve. Back in the day when the 3% rule first came in, I sat down with our design team I was working with at the time, and we were actually struggling to get a pump at 120 kPa to sit within that 3% rule. Nowadays, with advances in pumping technology and controller pumps and so on, that's actually dead easy to achieve even at 300 kPa. And so above 300, you start to come up against it, but generally you're okay. Any questions to this point, Duncan?
No, you can carry on, Chris.
Okay. So I'm going to talk a little bit about headroom connections. So we've got all these pipes coming up out of the ground. How do we header them up? How do we transport the water from the plant room, from the heat pump to the tops of the boreholes? And we've got quite a number of options. First one is a manifold. Now, a manifold, I'll draw it in plan view, is buried externally to the building, or could be inside the building on a wall, for example. And each borehole comes back to that manifold with a pair of connections. And inside the manifold, you'll be bringing those pipes together into a bigger header pipe. And there'll be valves, and there'll maybe be balancing valves and isolation valves on these as well to connect all these up. These can be either bespoke or off the shelf. Movitech are a fantastic supplier of these, and they're very, very useful, very, very helpful folk. And I know Kensa use them a lot. So that's one alternative, is the manifold. Okay. These could be under buildings, they could be in broom cupboards where pipes are coming up from underneath the building, all sorts of different locations. But from a domestic point of view, you'll generally see them in the garden outside, somewhere close to the bore field. And then the header connections come off of them. So that's your manifolded system. The alternative you've got is a thing called the reverse return. Now, if I can try and draw it for a 2 borehole system, imagine we've got our flow going out to the bore field and down the boreholes here, not in plan view anymore. We are in profile view. And if we connect the header like this, then what you can see is that if I walk from here to the end through that borehole like that, I'm going very close to the same distance as if I do it down that borehole like that. And so it's a self-balancing manifold, and it can be buried under the ground and forgotten about. So if you are happy with the resilience of having a single bore field, then this can be a very effective solution. It's particularly good for very large bore fields where it keeps the cost down dramatically, because, you know, obviously manifolds have a cost to them, and they're very simple systems. And, you know, one key rule of thumb in any engineering is keep it simple. And the reverse return can be a very, very effective and simple way of connecting your pipes up. No balancing required. The other point I make on manifolds is that because they've got valves in them, they are probably the primary source of leak in any system, valves. So your reverse return doesn't have the valves, so they don't need the valves, and therefore they don't have so many problems with longer term seepage and so on. You can actually hybridize between manifolds and reverse return. So maybe in a big commercial building, you might have a reverse return header going out here to, 10 boreholes, and another reverse return header here going out to another 10 boreholes, and then going back to a bigger manifold, which would then again connect them all together. So there are all sorts of different options between, in between. And I'll come back to why you would choose one or the other in a second. Inside manifolds, you can often have what's called a bypass. So if we've got a pressure drop problem in the collector themselves, then inside a manifold, we might have a 4-way manifold here, and our loops are effectively connecting like this inside. So we've got, say, 3 loops, and we've got one connection that goes between the 2 here, like that. And we've got some flow setting valves and so on and all of these along here. What we're effectively doing is allowing some of the water to go from the flow directly back into the return. So it's bypassing the loop with some of the flow. So why would you want to do that? Well, if you can't get enough flow to keep your heat pumps happy to go through these boreholes with a low enough pressure drop, then this can be one solution. Okay, it is successfully used, has been successfully used in the field. Setting these valves is actually very, very challenging when you've got a much shorter circuit here with a much lower pressure drop, and trying to get that balance of flow to give you your heat pumps a happy temperature difference across them can be quite challenging. So it is entirely possible to do, but it can be, as I say, challenging. Another point that was asked in one of the emails in the run-up to this discussion is flow setting. So say we've got, again, a manifold like this, and we've got a couple of boreholes here. Let's just draw it like this, slightly differently. So we've got a couple of boreholes, one here, that's going down into the ground this time, and one down here, okay? Connecting up like that. The pressure drop in this longer header element here is going to be higher than the pressure drop in this element. So if those 2 boreholes are identical in depth, you're going to have a pressure drop difference between the 2 boreholes. Now, because of that pressure drop difference, you're going to have a different flow rate here than you are here. This is going to be a higher flow rate, and that's going to be a lower flow rate, because the pressure drop here is higher and here is lower. So naturally, the water is going to take the path of least resistance. So what you'll have here is a set of flow setting valves that will allow you to balance the flow between the loops. I know an awful lot of people in the industry who obsess about this. You don't really need to be that close. I wouldn't start worrying about the differences in these lengths until you've got at least a 10% difference in pressure drop overall. And Leighton and Emily, our engineers, do spend time checking to see whether we're flagging a problem with potentially needing flow setting in that loop if we've got a borehole right down the other side of the site connected to the same manifold. So we'll tend to flag up, yeah, we're going to need some flow setting in this, and it's a little bit painful, but you're trying to get equal flow between the 2 bore fields. Okay, absolutely can't be done. Many manifolds are supplied without flow setting, just isolation valves, but many manifolds have got flow setting, and some have actually got flow meters in there. So the simple type of a meter you might see in an underfloor heating manifold, where a little bubble gets pushed up on a scale with the pressure in the system. So almost very straightforward to do, but you want to avoid it because it's just costing your manifold as well as just more hassle on site to get the balance right. And as I say, it's not that critical overall.
Lovely. Question in on reverse and return. Do you increase the pipe diameter to reduce resistance? Yeah,
so in any header pipe, what we're doing is we're looking to select that diameter of that pipe to make it acceptable within the overall context of the system. So for example, if we've got, like, I don't know, 40 kPa in the borehole, and we've got an 80 kPa pump in the heat pump, then we've got 40 kPa to play with for the pipes on the bends, okay? And so we might look to increase that pipe sizing in the header from, say, 63 mil to 90 mil, 90 mil to 110, try and keep the limit of the size of pipe that we use to 125, because 125 is the maximum that you can manually handle on site, but we can't go bigger. There are implications to that. So we've got this space in the middle, if you like, that we can fill up with the pressure drop in our headers, and that applies to manifolded systems or reverse returns. On reverse returns, though, there is a slight subtlety. So say we've got 4 boreholes, okay, here, and we are going to connect them all up with a reverse return manifold. So there's our flow in there, and there's our return. Forgive, we've got a few dodgy electrofusion joints in this drawing, but we've done our best, okay? So what you're looking at here is when you're actually trying to flush the system out, if you keep all of this pipe along here, the same size, then say at 63 mil with 4 boreholes, then you're trying to put all of the dirt, all of the air and everything else that's in this bit of the pipe down 140 mil borehole. So you're trying to squeeze 63 mil worth of dirt and so on down into a 40 mil borehole, which actually makes your flushing and purging very difficult. So what you tend to do on these is, as you go past a borehole, you reduce in pipe size, so that on that last run there, you're at the same pipe size as in the borehole. So the pipe work on a reverse return manifold, a reverse return header, is a bit more complex than the pipe work in a manifolded system, but perfectly doable. I've designed hundreds of them over the years, and in larger commercial systems, it tends to be the most ubiquitous solution. Any other questions on that to that point?
That's it for now.
Excellent. Okay. The key things that you are considering when you're looking at manifolds against reverse return is resilience. Okay. If you reverse return everything up, you might have 100 boreholes out there, 10 boreholes on a single leg of a reverse return, and 10 reverse return headers. So you've got, I won't draw 10 of them, but you've got something like this with boreholes connected in the middle, like that. And then you've got another one, and another one. And then you can actually put a reverse return on this, like that. Connect it back to your building, like that. Okay, there's boreholes in here, yeah. So you've just created a reverse return upon reverse return header. Nothing on the surface, no need for manifolds, no need for valves in it. Entirely doable, entirely feasible. But if you lose one borehole, you are going to lose that whole bore field. Now, why would you lose a borehole? Predominantly because somebody digs it up. Post installation, they just don't tend to fail. We have had 3 due to coal mines in the recent past on one site, but in something like 50,000 boreholes that I've designed over the years, that's the only 3 we've lost. I know of having been lost post installation. So it absolutely can be done as a total unitary system with reverse returns, and in large bore fields in America, particularly, it tends to be done that way. But you're not got any resilience on it. Right at the other extreme, you see this a lot in Scandinavian countries, mainland Europe countries, where they're taking, got 100 boreholes here and they're manifolding them all up into 10 manifolds, and each one goes back to a manifold. Or even more extreme and frankly dumb, you'd have 100 boreholes all coming back to a plant room in 40 mil pipes. Stupid idea. You'll see it on you'll see it a lot on in pictures and so on, of all these pipes running back from bore fields under buildings. As I say, massively stupid thing to do, and it's just somebody who doesn't know how to design ground loops, frankly, who would do something like that. So generally speaking, you've got a balance in the middle, whereas, maybe up to just doing one in central London at the moment that Ken's is hopefully going to add. And I tell him, I went over the knee of our managing director for mentioning projects by name last week, and he had to edit them all out because I wasn't supposed to. So a project in London where we've got 8 manifolds with 10 boreholes each, all coming back to locations around the site, and then with main header runs going back to the plant room. So you've got options to give you the level of resilience that you're comfortable with. And what I would just mention on resilience is the state of the art in terms of resilience is when you're beneath buildings. You really do have to consider, if you're installing boreholes under a building during construction, then you've really got to consider a resilience strategy very carefully and how you manifold that up, because you're not going to be able to access that borehole post installation. So quite a lot of considerations in terms of the headroom connections, what the size of the pipes are, what your configuration are, how you're piping it all up, how your pipe sizes get bigger as they're carrying more water back to your plant room. So any questions on that before I move on?
That's your lot.
Okay. So just a few words on pushing the limits. What do I mean by that? Well, we're continually trying and are continually asked to get ground source in more and more places. So tighter city centre locations. maybe more outputs out of systems and so on. So one of the things that we are working on is deeper boreholes. 300-metre boreholes was mentioned earlier on. When I first started in ground source, we were really limiting ourselves to 100-metre deep boreholes. More recently, maybe 10 years, 15 years ago, 200-metre deep boreholes started to become the norm. Many drilling companies can still only drill to maybe 80, 150 metres because of the equipment they've got. But the more equipped drillers will be comfortable drilling to 200 metres and beyond. So as we go deeper on our boreholes, what have we got there? We've got, for a given output, we might have had 10 boreholes at 100 metres before. Well, now, very, very crudely, we might have 5 boreholes at 200 metres before. So not only have we got longer paths, so longer pressure drop, longer runs to build a pressure drop, but we've got less parallel paths to put that water down. So the more parallel paths you've got, you're dividing the water flow rate by the number of paths you've got. So it goes down. So your flow rate goes down with more boreholes. So as you push deeper, you've got a double whammy effect, really. You've got fewer parallel paths for your water, and each path's longer, so your pressure drop starts to become more and more of a problem. So that's why deeper boreholes are, pushing the limits, not just from the point of view of installing them, but also hydraulically and how we design these systems. So the crude answer to that is go up a pipe size. So go from 40 mil pipe, which is common, to 200 metres. Rule of thumb, just to give you one, 100 metre deep boreholes, 32 mil pipe is generally okay. 200 metre boreholes, 40 mil pipe is generally okay, and deeper than that, you're definitely into 45 mil pipe. Occasionally, you'll sneak 40 mil pipe up to 220, something like that, but generally it's 45 mil pipe. But that's what we do, spend a lot of time doing calculations on. Okay, so deeper boreholes generally drive you into having pressure drop problems. New heat pump products are definitely worth mentioning. So we're involved in the new innovative products that are coming on stream from Kenza, and we're really excited about that. But I'm anxious to see what the flow rates are like on these things. So if you're chasing efficiency, if you're chasing the ultimate efficiency, you're almost always going to have bigger heat exchangers, which can handle bigger surface, which you've therefore got a bigger surface area, and generally will be flow rate hungry. So they'll be looking for higher flow rates on those systems. So that could drive you into pressure drop problems. If you're looking for the ultimate compact product, then it might mean that you've got quite a high flow rate and a very small heat exchanger, therefore quite a high pressure drop in the heat exchanger inside the product, like the Shoebox 6, which is, it's quite challenging to design for when you're talking about the pressure drop because it's such a compact box. So the heat pump itself can really push the limits of the ground loop design. Pump products, I can't remember if I mentioned this earlier, so forgive me if I'm repeating myself, but when I first came into it, to get a pump to deal with 110 kPa and stay within the 3% limit was quite challenging. But now we can go to 300 kPa relatively easily with modern pump products because the efficiency improvements have been such, and the product development in pumping has been such, so important. So pump products can help or hinder depending on how you see it. So just to mention then, as pumping increases, it's worth mentioning that the installed cost of those pumps increases. So the bigger the pump, the more cost it is. And if you've got a pressure drop problem, then buying a really expensive fancy pump can be a way of dealing with that. So again, installed cost as far as pumps is concerned is can be a casualty, if you like, of increasing pressure drop. You've also got the installed cost of the collectors, the pipes in the ground. 45 mil pipe costs more than 40 mil pipe, for example. The header pipes can also be made bigger. That can be a real challenge when you talk about particularly risers inside buildings. You've got physically how much space have we got to put those pipes inside the risers, inside the buildings. And, it's something that we work with the design teams, between our design team and Kenza's design team, to try and get those risers, the pipes to fit in the risers. Run cost is very important. So as pumping increases, it has a detriment on run cost, hence the 3% limit, because that's keeping it sensible. Robin Curtis famously shows a picture in one of his presentations about a stately home he was asked to look up with a 50 kilowatt heat load and the pump on that system was 25 kilowatts consumption on the pump to drive the fluid around the loop that was massively undersized in terms of header sizing. And once you get to that point, there's very little you can do about it. So it's very, very challenging. And then finally, hassle. You know, as pumping increases, it becomes more difficult to design. It becomes more difficult to install. It just becomes more of a hassle. So if we can design around just allowing the pumps to get bigger, then it saves us cost, it saves us hassle, and it saves us run cost. Any questions to that point, Duncan?
No, you're clear.
Okay. So just final bit, and then we can throw it up for questions, is the initial geology report. So when do we do an initial geology report? Really, as soon as you can within the project timescale. What we are doing in the report is to try and help you get a sale over the line. And why do we do that? Well, what we're looking to do is understand the geology and the thermal properties that we can work off the desktop for. We're trying to understand what the drilling conditions are likely to be, and are there any risks associated with drilling in that location. Next time we're going to come back and talk about risks in detail, so I won't go into it in much detail, but just suffice it to say, you know, water could start coming uncontrollably to the surface, for example. So we need to understand that as early as we can in the project, so you're not wasting your time trying to sell projects that are just not going to be practical to install. As part of the report, we also give a budgetary ground loop requirement. It's not going to be absolutely perfect, but it's going to give you a good idea about how much pipe is needed to go in the ground. And we also flag pressure drop problems early on in the project. So if we're looking at, you know, borehole pressure drop with what we've got on the table being 60 kPa, then that might be okay if we're talking about a big plant room system with external pumps, but in a domestic system, it really isn't going to leave you an awful lot of space for your headers and everything else. So we're trying to flag that pressure drop. Just finally then, how do we do it? It's a fully desktop process. We utilise the records from British Geological Survey, an awful lot of experience. We utilise test bores that we've done. I've got something like 400 test bore records available to us within our company, and I'm actually trying to negotiate with others in the space to share these records more readily, which is an ongoing process at the moment. But it's that intelligence that you're trying to measure up, trying to work with. And it's a detective story. It really is. You're trying to piece together the parts of the puzzle to get to the whodunit in terms of what's our thermal properties that we're expecting, what's our drilling conditions likely to be at that location. And just finally to mention, we always do an actual ground loop design. Previously talked you through a ground loop design at very high level. We actually do a ground loop design for every initial geology. And the reason we do that is I gave up guessing how much ground loop an awful long time ago. And the reason I gave up guessing is because I'm always wrong. So we always do an actual GLD on these initial geology reports. So that's the when, why and how of the initial geology report. It's there to help you close a sale with confidence that we're at least in the right ballpark as far as what we're installing is concerned. What can change between initial geology and a farm sale or a farm design? Loads of things. Borehole spacing probably being the key one, but also building loads tend to change. We might find we've got a riser sizing problem. So all sorts of things need to be built on top of that initial geology, but it's a very, very good start to equip the sales teams to land the jobs. Okay,